Afternoon. So I'll be giving a short introduction to the finite volume method, FVM, and I'll cover about the simple FVM, simple introduction to FVM, and the simple comparison to FVM and the control volume formulation methods. Okay, so in the finite volume method, it has a general equation that covers the following terms of diffusion, advection, time derivative, and source term, and they move in and out with a defined control volume as shown at the right here. So as we learned previously, control volume is a space we define ourselves and we allow some flux to go in and out. And the flux here indicates the items such as a fluid flow or even electrical flow that can go into a control volume and comes out. So control volume actually gives a good flexibility in analyzing the substance or species we want, depending on our studies, and as long as they can be defined as flux, they can be applied in the control volume. So here are some advantages of the finite volume method. So as we know that in a mesh, there will be a mesh refinement, and that this big square as a control volume, coarse control volume. So as we refine, it will be getting smaller and smaller and point. So as we also learned previously, in the FDM, as we reduce the sizes of the mesh, the truncation error will be refined as well, where we will have a lower error. So in FVM, the size of the control volume is independent of the error. Because remember that as we mentioned just now, what goes in will come out. So even there will be some errors that will be cancelled out by the in and out. So in a large control volume, as we have the different refinement, the error will be uniform because the errors are cancelled out. So we have a uniform error because the errors will be cancelled out by the in and out. So as contrast the FDM, because the difference in sizes of the mesh, the truncation errors will be varied. So the errors are dependent of the mesh refinement, and the errors will accumulate along the meshes. So I'll give some intro to the generation of meshes. So there are three types of generations. First is the rectilinear, which is the using the dots here. So when it captures a curve geometry, like I showed at bottom here, it cannot show the smooth curve, and it only can show the step figures at here. So for our CFD simulations, we have to input our boundary and also the input conditions. So since the boundary are not as good as we want, so the accuracy may be lower. So move to the second generation is known as the curvilinear. So the meshes here are made by depending on the boundary of the shape here. So you will see the variation of the mesh is actually following the boundary, where we have the curve and also straight line here. So this type of mesh actually has a lot of problems, especially in capturing complex geometry. So since it is the boundary defined, so if the boundary is very complicated, the meshes cannot be generated. So let this semi-hemisphere, this quarter here. So assume that we extend the mesh here. So this actually is not possible it is possible, but it will be problematic because as you see, everything ends at one point where we have to define the directions. So if everything goes to one point, there will be some problem. So if I'm not mistaken, this is known as singularity, which is not desired. So lastly, we move to the third generations, where is the unstructured mesh. So it gives a good flexibility in capturing the geometry, both square and also the curved geometry. So this unstructured mesh is applied for the control volume method for the formulations. So we have two types of method, which is the cell-centered and also the direct-centered. The cell-centered here means for one element of the mesh, the unknown is placed in the center of the cell. While for the vertex, they choose a point where few elements share the same node, share the node in the middle. Then they form a new control volume and use this point as the unknown to calculate the simulations. So that's all I'm to cover. So thank you very much for your time. So is there any
Thank
questions?
you so much, Siu.
Okay.
Okay, so now I open questions for all students. Remember, those who ask questions will get bonus point for this session. So I encourage everyone to ask. If you want to ask question, could you please state your name so that I can take your names and put it in the system. All right. So please state your name clearly and ask question. Okay. So please proceed. Anyone who has question to Siu?
Yeah, this is Ashikul.
Okay, Ashikul, please proceed.
Yeah, Siu, I wanted to ask about mesh generation. If we can go to that slide number 4. Yeah, so as you mentioned, like first refinement, second refinement, and third refinement. So based on what we can refine? Is it higher order term or how we refine this?
Oh, it's actually not refinement, it's the generations of the mesh. So throughout the evolution of meshing in the study, they first start off with the first generation, and they evolve through the curvilinear and also the unstructured. So this is actually is how they improve in capturing the complex geometry. So this is actually not the refinement as mentioned previously. Good.
So how can we generate like after first, how can we generate the second one?
Oh, I think this will be depending on the software you use, because I personally experienced on generating the curvilinear mesh, where the name of the software is known as Gmesh, where you can define and draw your own meshing. So for this type of mesh, you have to define, if I'm not mistaken, at least four lines here, like first one at here, second one, third one, and the fourth one. For curvilinear type of mesh, you need to define your boundary first, because the mesh is dependent on the boundary. Well, for the others are actually quite easy. You can just pick the type of mesh like etc. You just pick the control volume you want and you just apply the mesh.
If I can clarify a bit from what Siu just explained. So
yes,
what Siu explained is particularly what Ashikul was asking about refinement, but this is not about refinement. It's about how the mesh setup progresses from the first generation, which is just a rectilinear or just square grid, and then the square grid is advanced or evolved into the second generation, which takes into account of the curvilinear shape. So curvilinear means you are still dealing with kind of a structured grid. As you can see over here, is the shape is kind of rectangular plus squared, but now it has more advanced features that at least can capture a bit of complex geometry, as the figure shows for the second generation. And now, as the computational resources, as the technology evolve, we are now entering into the third generation, or the latest one, which basically enables the finite volume method to be used on unstructured grid. So as you can see here from the figures that Siu showed in his slide, for the third generation, we can now mix both the rectilinear plus the unstructured grid. So that's the advantages of the finite volume or control volume methods. And as I think the second question, how do you generate this? And then Sue already answered, it depends on the mesh. So the one that you were using Gmesh, was that for your FYP, Sue?
No, it was during my internship with Dr.
Okay,
Isha.
during internship, good. Good. Okay, so so what you mentioned was again spot on. So it depends on the mesh software. Depends on the software. So as you understand, each software requires or accept a certain type of mesh generation. Okay, so for example, once you move away from commercial software, from for example NSYS, NSYS is quite convenient to be used because it has in-house mesh generation. But for open source software, mostly they don't have the meshing capability. They requires mesh to be used or to be generated outside from the system. So for example, by using the Gmesh software. Okay, so mesh can be generated outside from the main software and then can be imported to be used on the software itself. Okay, hopefully that answers Ashiku's question. Thank you, Sue. Thank you. Okay,
Sir.
anyone
Thank you,
else
Doctor.
has question for
My
Sue?
name is
Very good
my name is
explanation, Sue. Anyone else?
my name is Ijmal.
Ijmal, okay, please proceed, Ijmal.
As you present just now, you said the FVM use the flux properties in going in and going outside from the control volume. Can we see the cell centered and vertex centered? Slide number 5. Okay, can you show me a little bit, can you show us a little bit how the flux going in and out between these two cell centered and vertex centered? Thank you.
I think it's so everything will be going in and out of the boundary. So we just have to define at the boundary here what is going in, what is going out. Because remember, we are using control volume. So we just have to define at the boundary what is going in, what is going out. If I'm not mistaken, this is the simplest explanation. Just go back to the boundary.
So basically the flux are defined by the user lah.
Yes.
Okay, thank you.
Like if you want to analyze fluid flow, you just put fluid.
Okay, thank you, sir.
Okay, welcome.
The flux, just to clarify, the question from Ijmal just now, the flux, was it defined by the user? The flux itself is not defined by the user. For example, as you said, if we want to calculate, for example, the heat transfer or the fluid flow from one cell to another, it's not one cell, from one system in the system. So the flux refers to the energy, to the fluid equations that is being calculated. So the flux is in terms of energy, it can be in terms of the flow. Then is not the software, the equations that is being calculated, okay, it will be calculated on the elements in the blue color here, as shown in the pictures over here. Okay, and so this element can be in terms of cell-centered, meaning that we have one cell, and then the calculation will be done in the middle, in the dotted here, the purple dot over here. Okay, thank you, Sif. You can use another color, yes. So in the middle here, the one that is used coloring right now, the yellow color, that's where the equation is being calculated in the middle of the element. Okay, in contrast, when we look at the vertex centered, so what happens now, instead of just one element, the center of the calculation, okay, is now consists of several other elements. So as you can see here, Sue's already labeled them. We have 1, 2, 3, and 4 elements. Okay, so that's, I think, depending on the software or the equations that we use. Okay, so again, if you look at these two very simple examples, but I think again it relates to what we have learned. Since the element, since the dotted note over there is located in the middle of the elements, it shows that we need to have our element to be refined, or at least should be enough to allow the calculations to be as accurate as we can. So for example, if our element is too big, so what will happen? The calculations basically will be done, or will take the average value from one element on the left side, for example, and then another element on the right side, and it takes the average value of it and calculated in so that it is centered at on the element. So if our element is too big, then the average value that is calculated in the middle of the element will not be accurate. And since we have calculations on the large element, it is not accurate, then the value of the inaccurate flux will be transferred to another element. And then this again will proceed to another element, to another element. In the end, it will affect your calculations. Thank you so much, Sue, for helping to illustrate this. It's kind of like having an assistant to do this description. Thank you so much, Sue. Okay, again, I think we have quite a few interesting questions from students. Anyone else? You got any question from Sue? For Sue?
Me, this
Okay,
Sophie. I
if
just
there is
want to
no
ask a quick question.
Sophie.
I want to know when is cell-centered is used and when is vertex-centered is used. I mean, it's under the same category, right? So when is it used?
I think it's depending on the user.
Depending on the what? Sorry.
Depending on the user, like which you prefer, because there must be some advantage and disadvantage for them. So it's depending on the user.
All right. So what is a suitable application for cell-centered and then for vertex-centered?
This I haven't covered yet, so I think you can consult them.
Right.
Sorry for the question.
Okay, thank you. So Alam, from the question from Sophie is very, very valid. And I think, yes, I agree with you. It depends on the user, but it's not depending, for example, like you can choose the algorithm or the options, just as simple as that. As I think I explained this a bit in the class, whenever you use a software, for example, let's say NCS. NCS, when we buy NCS or when we downloaded NCS and we use it, the developer already defined which discretization method, for example, or which mathematical formulation that they want to use for their software. So similar to this, for FVM was control volume method, the choice of cell-centered or vertex-centered, again, is not something that, for example, you use a software and then you decided, okay, I want to use vertex-centered. It's not like that. So pretty much, usually the developer of the software has already decided, okay, for this particular software, we are going to use, for example, vertex-centered. Okay, okay, and then I think the second question from Sufi, when can you use cell-centered and vertex-centered? I think that's a very, very generalized question that even I think I have no simple answers for that. When can you use for one and when can you use for the other one? I think let's KIV for that. I'll try to find an answer that should be suffice to make it to help you understand the comparison. So I KIV for that. Hopefully we can cover it in the next lesson. Thank you, Sophie. Okay, I open one last question for you before we move to another student. Anyone? Okay. If there is no other question, thank you so much, Sue, for your explanation. Okay, so now let's proceed with the second presenter, which is Shahirunisa Ramli. All right, so please, I invite Shahirunisa. Thank you, Sue. Okay, Shahirunisa, whenever you are ready, please proceed. Shahirunisa, you can proceed whenever you are ready. Hello, Shahirunisa. Hello, can you hear my voice? I cannot unmute myself. Oh, okay, let me check. Shahirunisa, just 1 second. Shahirunisa, Shahirunisa, where's Shahirunisa? Okay, let's try. Okay, how about now? Okay, yep, we can hear loud and clear. I think I mistakenly mute yourself. Okay, please proceed. Thank you.
I hope that you guys can see the my screen.
Yes.
All right, thank you. Good evening, everyone. Good evening, doctor. So I'll be explaining a bit in finite volume methods, which I take this reference from the computational methods for fluid dynamic by Freysiger Perry, the one that the doctor advises to for the material additional material. So here's the thing where the finite volume itself uses the integral form. This is the integral form, which is the equation of 4.1. This is a conservation of equation. So means that this solution domain is subdivided into a finite number of a small control volumes, which we call it as a CV, by a grid. Means it will, in contrast to the finite difference method, and the next one is to define the control volume boundaries, not the computational nodes. So the integral conservation equation for 4.0 is actually applies to each of the control volumes as well as to the solution to the domain as a whole, which if we sum up the equations for all CVs, we will obtain the global conservation equation. Since surface integrals over the inner CV faces to cancel out. So means that global conservation is built into the method, and this provide one of its principal advantages. So how do we define the control volume or CV, which this usual approach is to define CV by using a suitable grid and assign the computational node to the CV center. As the given figure, I've noted A and also B, they look alike, but actually it has a very small difference over here, which all right, so for the structure grid, we need to define the nodal location first, and after that we construct CVs around them so that the CV face lie midway between the nodes. So in the figure A, it shows that the nodes is centered in CV, control volume. While in B, we see that the CV faces centered between the nodes. So actually it has different over here. So here, I can see the difference over here. Like it took me like hour to find the difference between these two pictures. Then after that, I realized that there is actually a difference between these two. So next. Okay. So though there are several other specialized variant of every type methods, some of it are cell vertex schemes, dual grid schemes, and etc. However, in this time, we found that this is the basic method that have specific advantages, which the first approach, this one is A. The nodal value represents the mean over the CV volume to the higher accuracy, which is the second order, compared to the second approach, since the node is located at the center of the CV. Then the advantage of the second approach is that CDS approximation of derivatives at CV faces are more accurate when the phase is midway between two nodes. Figure below we have typical 2D and also 3D Cartesian control volumes, which show that we use together a notation. As we know that for the CV surface in 2D, we have 4 plane faces, while for 3D we have 6 plane faces. So these to be specific according to this figure. So it also been denoted by the lower cases from E, W, and S, T, which it is respect to the central node. We point it central node as P over here. So the 2D cases actually can be regarded as a special case of the 3D one, in which the dependent variables is independent of Z. To be in details, 1D and 2D also will be discussed by the next presenter. However, I will just be touch these few things that I found that it is important at one particular point. So in this follow that typical CV phase, it is also labeled as E, if we can find here. Yeah, it is labeled as E. Which it will be considered as analog expression may be derived for all phases by making appropriate index substitution. So to calculate all those surface integral exactly, it needs to know the integrand of F everywhere around the surface of SE. Actually, this information is not available as only the nodal of CD center. So the value of phi is calculated approximate. It must be introduced approximately. So this is the best done using two level of approximation, which the first one is the integral is approximated in the terms of the variable values at one or more location on the cell face. And the next one is the cell phase values are approximated in the terms of the nodal, which is the CV center itself. So I think that's all for my part. Yeah.
Thank you so much, Lisa, for your explanation. Quite technical. Okay, very good. So informative. And now I open the floor for anyone to ask questions. I would encourage students other than the one who just asked question for Sue. If possible, other students than the one that asked. I think the one that asked just now, Ashikul, Ijmal, and Sufi. So other than the 3 students, I open the floor. Please.
Najiha.
Yes,
Hello.
please proceed,
Yeah.
Najiha.
Okay.
Please. Okay.
Shah, how to evaluate flux at control volume corners?
Okay. Thank you, Jiha. For evaluate the flux at the CV corners, it actually has a higher order approximation of the surface integral. So means that a fourth order of approximation in the Simpson's rule, which it is estimate in the integral over SE as a, it has actually it has equation which FE is integral of SEF ds. How to write now? Actually, you guys can refer to the equation of 4.5 at the textbooks of Verziger Period 2002. I guess that one is will help you guys. This reference book and the equation of 4.5. I hope it answered the questions.
Alright, thank you. Senang je answer Syah. Kita please refer to equation 4.5. Okay, selesai. Okay, thank you Syah and thank you Aina for the question. Okay, I would like at least 2 or 3 more questions for Shahrunisa. This is very good. Please, any other students?
Good evening, doctor. My name is Naren.
Come again?
My
Naren,
name is
okay,
Naren.
please Naren.
Doctor, from slide, how to define the control value? Can you go to the slide? This one.
Mm-hmm.
So from these two figures, how you identify the difference? I cannot get it.
Right. Same like me. Thank you.
Thank you.
Because as I said, it took me like 2 hours to realize and differentiate these things. And also, doctor, correct me if I'm wrong, but I can see that it has a very small differences where I said just now, the notes on the left side is centered in CV, while the B, which is the right side, the CV faces centered between the notes. If you can see, this part and this part is actually different. You must take the ruler to see the difference, I guess, because it has a very small differences over here. And I thought by this it gives a big difference to how to define the volume. I mean, in the terms of the notes, it has been centered in CV, and also the CV faces centered between the notes.
So,
what?
Shah, is it moving forward?
Sorry, proceed, Naren.
我按照另外一个色，然后把线没有调出来，然后它身上这里没有带过。
Sorry, is Naren asking or is there anyone else asking questions? Okay, just to add what Shahrunisa just explained, the figures basically used in the textbook between A and B, that's not a very good representation, honestly, because they do not exaggerate the difference. The difference should be, how should I say, it should be simpler or easier to be detected. But as Shahrunisa said, the figures basically shows a very, very, very small differences, which is quite hard for us to see with naked eye. Okay, so but what Shahrunisa said is right. The one for A, based on figure A, the notes basically it shows the notes, the white note, it is located at the center of the CV, meaning that you have a control volume, the structured grid, and the note in the middle, the calculation point, is located right in the middle. Okay, but for the second one, for the control volume for B, the CV faces centered between nodes. Okay, this refers not in the middle of the grid, but now the nodes that is surrounding the structure grid. Betul lah my explanation, Shahrunisa? Kena tanya cikgu.
Betul.
So yeah, again, as I said, this figure basically does not do justice lah for us kalau yang first time reader tu, because it's very very difficult to detect the differences between A and B.
Betul.
Okay, alright. Okay, so
Okay, thank you.
No, Najiha, not Ainur. Okay, sorry Nurul Najiha. Betul. Saya confused. Saya ingat Ainur tadi. Thank you. So Nurul Najiha.
Hello, this is Sim. I have a
Alah,
question.
you pun nak tanya.
Okay, yes.
What will happen if the node is not in the middle of the element?
What will happen if the node is not in the element?
In the middle of the element.
I had to be truth over here. I think I cannot answer Sue's question. I'm sorry.
Don't worry, we have doctor here.
Okay, so from my understanding, Sue was asking basically what happens if we have the node. So I think the node here refers to the dot, a white dot, Sue. Basically the calculation point. Betul Okay. So basically the calculation point, I call it calculation point lah. It has a different term, but for the sake of argument, let's call it calculation point, the white dot. Okay, aside from the middle of the control volume, okay, as B showed, it can be the middle of the nodes. Okay, aside from these two, the calculation point can also be on the it's not the transition, on the element face, meaning that right now it's in the middle of the element. So the nodes, the calculation node can also be located in the middle of the element face. Meaning that Sharwinsa, if you can just make some sketch boleh tak yang dekat red dot, black dot tu. You can make some contohing sikit, ada use yellow color ke like you just now? Yes. That's the element face. So again, it depends on the mathematical equations or the methods that is being used to calculate the variables or the flux of the control volume. It depends on the developer. Because, for example, the software that I used previously, basically we have two options. One software uses the control volume, which calculated the fluxes, being calculated in the middle of the element, while the other software which use the control volume as well, but now the flux were being calculated on the face of the element. So that's other variables or other options for this method. Okay, thank you. Thank you, Sue. Okay, one or two more questions for Sharwinisa. Very good presentation. One or two more questions for bonus mark. Okay, if there are no other questions, thank you so much, Cikgu Sharwinisa, for your sharing session, and also Sue just now. Okay, so let's move on to our last presenter for today, which is Ahmad Abdullah Ahmad Badugash. Okay.
Yes, Doctor, can you see?
Yes, very clear. Usually when I see a desktop like that, it's usually for it's okay. I'll explain later. Okay. Please skip. Okay. All right. So the floor is yours, Badugash. Okay.
Okay.
Proceed.
Assalamu alaikum. Good afternoon to everyone. I'm gonna talk about. Sorry. I'm gonna talk about the.
It's okay. Please proceed.
I'm going to talk about the finite volume method, the equation for the 1 dimension and 2 dimension. So at the beginning, imagine that we have this problem. This problem starts from A to B. So from this problem, we will get this equation for the first for 1 dimension for the finite volume method. D over dx gamma d theta over dx plus s equal to 0, where gamma is the diffusion coefficient, s is the short term, and phi is the value of the boundary from A to B. So to solve this problem, we have some steps. So first step that is grade generation. In this step, we need to divide the domain into discrete control volume, as we can see as here. So right now, imagine that we want to calculate this point B. So this point B is surrounded by a point here in west side, and we represent it as capital W, and another point on east side, and represent it with E capital. And this point, also our point is surrounded with a control volume. So we represent it with a small w from the west side and E small from the east side. So the distance between P and capital W is delta X WP. The distance between P and E, delta X PE. The distance between P and W is delta X small WP. The distance also the same here, delta X P small e. The distance between small w and small e, which is our control volume, is delta x, which also equal to delta x small w small e. So the next step is discretization, and we need to edit the integration of the control volume for the whole equation. As you can see here, this is the first part, integration for the control volume d over dx, gamma d theta over dx dv, plus integration for control volume s dv. It will equal to gamma a d theta over x for the e small point here, minus gamma a d theta over dx for the w small here, plus s dash delta v equal to 0. And the s dash is represent for the average value of the source s, and delta v is the volume. So as we proceed with this equation, for the gamma w small w, we can calculate it by gamma capital W plus gamma p over 2. It will be the midpoint between the gamma p and gamma w. Same here with the gamma small e, gamma p plus gamma e divided by 2. And so from this, we can just substitute this elements, gamma a d theta over dx for e point. We can represent it as gamma e ae theta from e capital to p over delta x pe, and the same thing for the w point. We can represent it as the same thing, gamma w aw theta p minus theta w over gamma over delta x wp. And for s bar delta v, we can just represent it as su plus sp theta p. So at the end, if we just take all these equations and just replace it here, it will just give us this equation, the final equation, gamma e ae theta e capital E minus theta p, and the rest of the equation. So if we just rearrange the equation, we will get this equation with the representative of everything. And so to make it in shortcut, we just represent the whole thing inside this bracket as AP, and inside this bracket as AW, inside this bracket as AE. So at the end is gonna be like this one. So AP is represent to AW plus AE minus SP. Is it like this one? It will be like this one, but this is for the short term. Also for the AE gonna be this one, and AW gonna be this one. This is for the first, for the 1 dimension, and this now we're gonna go for the 2 dimension. It will be almost the same, but this time imagine we have this problem. Also, we want to calculate point P. In the previous one, in the one dimension problem, we just only had point W and point E. But now we have 2 dimensions. So we have W, E, N, and also S. So we have 4 points gonna be surrounding our point. So our equation gonna be like this one: del over del x, gamma del theta over del x, plus del over del y, gamma del theta over del y, plus s theta equal to 0. This first part is represented with x, and the second one with the represent of y. So the same thing that we're gonna do is to do the integral for the control volume of our space. As you can see, this is the dark square, here. The same thing. It's w, small w, small n, small e, small s. It's the same thing with one dimension. So we will get from this equation, we will enter integration delta v del over del x, gamma del theta over del x, dx dy, plus integration for control volume del over del y, omega del theta over del y, dx dy, plus integral of control volume s theta dv equal to 0. But right now, let's just notice something. Notice that the area for AE, this is the area for AE, it's the same area for AW, and also it's the same area or the same value of delta y. Same thing with AN, the area for AN equal to the area of AS, also equal to delta x. So from that, we can just rearrange this equation after we integrate. We can just represent it as like this one: REAE del theta over del x for E point, minus, this is E point, the initial, the final one minus the initial one, minus gamma W AW del theta over del x for the W point. The same thing for the for y direction, gamma n an del theta over del y for the n point, minus gamma s as del theta over del y for the s point, plus the same thing that we had in the one dimension, s bar delta v equal to 0. So this is our equation that we got just right now. So for a flux according the west phase, for gamma w aw del theta over del x, for the west phase, we can just represent as gamma w aw, as we said that before, theta p minus theta w over delta x wp, and the same thing will be for the rest of it, for the east phase, south phase, and north phase. So at the end, we will get, we will, if we substitute this equation into our equation, so we're gonna be gamma AE. So we represent with delta theta with theta A minus theta P, and delta X, which will equal to delta X PE. Same thing with the W phase, N phase, and S phase. So after we got our equation here, so this is our final equation. But after we rearrange the equation a little bit, it will just give us like this one, with the represent of theta p, phi p, and phi w, phi e, phi s, phi n. This is the representative gonna be. So the same thing that we did with the one dimension diffusion, we will represent it as AP, AW, AE, AS, AN. The same thing. AW gonna be represented for gamma W, AW, delta X, WP, and the rest is the same. Thank you. This is all from me. If you have any question, you may ask.
Hello, Rakesh.
so much, Pak Yogesh. I agree with Ijmal. Very nice presentation, like watching YouTube lesson. I totally agree with Ijmal. Very good presentation, Pak
Thank you
Yogesh.
very much,
Okay,
Doctor.
now I open the floor. I open the floor for questions from students to Badukesh. Very, very good information. Okay. Anyone would like to ask question?
Badukesh?
Yes, Tava.
I'm Deva
Yes,
here.
Stefan.
Okay.
Yeah.
Badukesh, can you go to the second slide?
This one?
Yeah. All right. Badukesh, can you explain to me where is exactly the source term? I mean,
Sorry?
for the entire calculation, we were using the source term, right? The S.
Yeah.
Where do we exactly can see the S in the entire projection here?
You mean the source term?
Yeah, where does it come from, the source term?
Source, the source from the source term gonna be from your system. This is the system that you want from it, and the source term will be from the part that you want to calculate from it.
Okay, let me try to explain
So,
about source term.
is it from the control volume that have been stated here, or the
Sorry.
Okay, let me try to explain that. That's okay. Let me try. A very, very good question from Deva. I was going to touch about source term later, but since Deva already asked, so I'll try to explain it to everyone. Okay, so when you are dealing with this equation, and Badukesh already mentioned, the term, the S term refers to the delta term, the source term, the S. Okay, so can you go back? Okay, yes, this one, thank you. All right, so if you look over here, the S bar, that's the average value of source term, but the question is, what is source term basically? Okay, for those who doesn't know, even in the Navier-Stokes equations that we covered before, there is a part where source term should appear or should be covered as part of the complete Navier-Stokes equations. So the one that we covered in the class or in the lecture last time is the fundamental Navier-Stokes equations. Okay, so when we talk about fundamental, meaning that it solves the basics equations, or it solves the basic problem when we have about the fluid moving problem. Okay, anything that is moving fluid, then it can be solved by using the Navier-Stokes. All right, but when we are dealing with a more complex object, okay, for example, when we have to introduce a problem inside the fluid. For example, if you want to check, if you want to introduce turbulence, okay, let's say we have a very, very smooth fluid, okay, flowing in a channel. Now suddenly we want to introduce some kind of turbulence in the middle of the channel. Okay, the introductions of the turbulence can be done by using this part, the source term part. Okay, S. So similar to Navier-Stokes as well as the control volume equations that we have over here, any introduction or any how should I say, if you want to introduce anything inside the moving fluid, for example, when we are dealing with Navier-Stokes, we have to do it using the source term punya fraction. Okay, similarly, when we are dealing with the control volume, if you want to introduce, I give you one simple example. If we are dealing, for example, for this control volume, let's say we are dealing with a heat transfer. So let's say if you want to introduce something in the heat transfer, okay, instead of just looking at the propagation of the heat transfer from the higher gradients to a lower gradient, now you want to introduce, let's say, suddenly you have additional heat source. Okay, so you want to introduce that heat source into the heat propagation. So that can be done at this S bar delta V part. Okay, so what we have over here is just the whole equations. Of course, when you want to introduce the source term, it needs to be done via a subroutine lah. Basically, it has a more detailed subroutine, usually a programming part, where we have to indicate, okay, to the software, okay, I want my source term, this part of the problem, okay, I want to introduce turbulence as my source term. Okay, this is where I want this turbulence to be included in the software, in the calculations. So I think I'll try to share what I did for my study, for my PhD study in the next class. Basically, it's quite related to what we are discussing right now, source term, as well as for the turbulence model. So, so I made some notes over here. So show or share source term. Okay, so I'll try to explain or to show as an example of how we introduce the source term in the software. Thank you, Tema, and thank you, Badugash, for trying to explain. Okay, I think we can get one or two more questions. One or two more questions. Okay, from Fahan. Okay, Badugash, can you have a look? What about the volume that is located at the edge end of a model? This is the control volume that I understand so far. Okay, very, very good question. One control volume needs two nodal. Okay, Badugash, can you try to answer question Farhan?
Okay. So what about the volume that is located at the edge end of the module? Since for the control volume that I understand so far, one control volume need two nodes. Yeah, that's right. For example, in this question, in this example, sometimes that he give you like the location for W, capital W and capital E, but he will not give you the location for small w and small e. So to get this value, we're gonna use this one, this equation, gonna meet the midpoint between P and W to get the value for our control volume, the beginning and the ending of our control volume area. Hope that answers your question.
Okay, not quite, Badugash, not quite. Okay. So the question from Farhan, the volume is located at the edge. Okay, let's assume we have a static problem. Okay, so for example, Badukesh, can you help me to draw like a static to draw the wall on the left side of A? Okay, at A here. Okay, yes, like static, good. Kind of like a wall. All right. So I think Farhan, correct me if I'm wrong, Farhan. So the question from Farhan, what about the volume that is located at the edge, basically located right at A, which is touching the wall? Okay, because there is no volume, because I think from the discussion that we had today, we can see that the main difference between the FDM, finite difference, and also finite volume method is that on the calculation part, for the finite difference, we are using the nodes to calculate. For example, if you want to calculate P, so we use the node W. Okay, for finite or the control volume, we relies on the volume. Okay, so right now, for the question related to Farhan, Farhan was asking, what happens to the volume that is located, that is touching the wall at A? Betul Farhan, am I right? Okay, so because right now from the discussion that Badugash just explained to us, he's dealing with the volume past the edge, meaning that after the edge or after the wall, then that's when we start doing the equations, yes. Okay, so now, for that particular problem, we have a very, very simple solution that you guys already know, which is in the software or in the calculation analytical solution, you need to specify the initial value. Yes, what happens if W is the edge? Yes. So that's why we need the initial value or initial condition. Because at that point, there is no calculation can be done because the control volume requires information from the previous volume or previous element. Okay, since the first element is located at the edge or touching the wall, so let's say, Badukash, can you just write down A as, let's say, U0, U0. Thank you. Okay, so that means that's the first part or the first step in our propagation, in our problem. So to do that, because we have no value or no calculations can be done at that point, that's when we need to specify our initial condition or initial value. Okay, so from there, when we define, let's say U naught equals to 1 meter per second or 1 watt, for example, kalau heat transfer in terms of what's the unit for heat transfer? The unit for heat transfer, anyone? Okay, so okay, whatever it is, let's say we have the 1 watt, for example. Okay, so that's our value that will be used to propagate to the next element, which will then be used to calculate the corresponding information. Okay, so I hope that explains or that answers the question from Farhan. Okay, so basically the problem is if you want to start from the wall, from the edge, what should you do? Okay, then you need to specify the value for U naught, the initial value or the initial condition. Very good question from Farhan. Thank you. All right, I think one last question from students before we have a very, very quick discussion on our quiz just now. Last question from students. Okay, from Ainur. To use the 1D steady state diffusion method, is there any assumptions we need to apply apart from 1D and steady state? Okay, very good. Badugash, can you try to answer this?
Yes, it will. I think it will depend on the question. The question gonna be give you some assumption you need to do it. But other than that, it will be the same assumption that. Sorry. But other than that. But other than that, it will be the same assumption that we just made.
It's not.
Can you hear me, Doctor?
Okay, can you please repeat your answer just now? Your reply?
Yeah. I said that I think it's gonna be depends on the question that they're gonna give you the assumption. Other than that, it just be the same assumption that we just presented as here for 1 dimension and also for 2 dimension.
Okay, I think yes, that's correct. Basically, apart from 1D and also steady state, I think the assumptions is presented here in the equations basically. Okay, we assume a certain condition, okay, where basically, as you can understand, we try to simplify our problem. Okay, and this simplification is being summarized by this equation basically. Okay, so that's from Ainur Najiha. Thank you. Okay, I think I have to stop our discussion for today. Can we spend another 10 minutes for a quick discussion on our quiz just now? Boleh ya? All right. So again, thank you so much for the presenters. We have Siu, we have Shahirunisa, and also Badugash. Very, very good presentation, which exceeds my expectation. So now we have next group presenters for next week. I think they have to do better than this. Okay, they have to challenge what these 3 students just presented. Very, very good presentation. All right, thank you everyone. So let's have a very, very quick discussion on our quiz. I'm not sure what happens to Larry. I texted him in the group, but he didn't reply because he's the only one that hasn't submitted his quiz. Quiz. Not feeling well. Okay. Okay, he's not feeling well. If that's the case, I think let's just discuss this the quiz to next week lah, next class. Okay. So all right, so I think that's all for today. Thank you very much, everyone, for your participation. I'll see you all next week. Please don't forget for the asynchronous session, have a look at the slides or the lecture PDF that I've shared. We are going to use that materials for our next class. There will be no attendance taken today, no form, because I will use your quiz submission as your attendance. Thank you very much, everyone. I'll see you next week. Assalamualaikum and very good afternoon.
Thank you, Doctor.